Hello and welcome to my channel again. So today's video's topic will be fine and hyperfine structure of the hydrogen-like atom, lecture 2. On the previous lecture, what we have already seen is that starting from the Dirac equation, we have already got a particular form of our Hamiltonian which is responsible for the fine structure. Basically, hyperfine we will do it later, where the magnetic moments will come into our account. But for this case only, we will discuss different interactions between electron and the nucleus, but not the magnetic one. Okay, so what we'll have to do, we'll apply an external magnetic field to our system, as we have seen on the earlier video, and we will set the B equals to 0 for our relevant cases. The B equal to 0 will give us the fine structures based upon the theory we have already discussed, and the B not equal to 0 case will give us the Zeeman effect terms, like the anomalous Zeeman effect, normal Zeeman effect, or the Paschen-Beck effect. Okay, we will derive the every correction possible of every corrective term or every perturbation term, excluding the H0, because H0 will be basically the Bohr Hamiltonian, which will give us the Bohr energy, and we already have solved this on basic courses, so I will not do that, and the rest terms I will individually solve. So today's video is basically, in today's video I will cover the part where we will get the individual terms, like this term will have the spin orbit, this term will have the Paschen-Beck, this will have the Zeeman. So we will distinguish every term possible, because in the last video on a place where it was in the midway. So I will just clean my board and start with the video. So as you can see that I have already written the equation 6 from the last day. I am basically maintaining the number of equations from the previous video. So this was the sixth equation, and I have ended the last video here. And the only thing I have changed here is the V of R was on my left, and I have taken it on the right and made this look like the unperturbed Hamiltonian. Okay, on the last we will assume, or we will define this as not assume, we will define this as the unperturbed Bohr Hamiltonian, which will give us the minus 13.6 by n squared the energy, and rest of this term will give us the possible corrections. Okay, and now we will find out or simplify this expression to find out the individual Hamiltonian. Okay, so let us start from this third term. Okay, third term, because this is the like big chunk, and the main fine structure will come from this. Here what we basically have to do is basically apply some vector rules, formulas of vector algebra, and we will get our necessary result. So h cut square by 4 m squared c squared, we will take this sigma out. Okay, the sigma dot with whole thing is basically now grad will act on this whole thing. Okay, so I will take the phi in. So this will basically give us grad of A and B. Okay, grad of AB. So I will apply this, and we will get finally grad will apply here first. This will give minus gradient of VR with sigma dot gradient of phi plus. Now grad will act here and will give us grad. Now already this is a scalar, so it will remain grad, not divergence, gradient of sigma dot grad phi. Okay, and now as we will see is that 4 m squared c squared. Now this V of R and phi of R, all of them are R dependent terms. So the only term inside the grad that will survive is R dependence. So basically del R cap will survive, and theta phi term will go to 0, because it is not a function of theta phi. So we will keep that in our mind, and we will start. So sigma dot minus sigma dot gradient of VR and sigma dot gradient of phi plus sigma dot grad, I will take the phi outside. Okay, we have to alter the way depending upon the terms. Okay, so h dot squared 4m squared c squared. I will take this term on the first. Okay, so on the previous video we have seen that sigma dot a sigma dot b is basically a dot b plus I sigma dot a plus b. Okay, we will apply this here and here too. We will get grad square phi of r. Okay, the del cross del will be 0 because it's an abelian cube. Okay, minus yes, gradient of Vr, gradient of phi r minus I sigma dot. The minus is getting transferred here, otherwise if I put a bracket then it will be plus I sigma dot gradient of Vr cross gradient of phi r. Okay, I hope this step is clear. So finally what we will get now, this is the vector, this is the vector, so I will put a dot here, and the only r dependent terms are there. So basically del v del r r cap dot del phi del r cap dot r cap is 1. So it's basically del v del r del phi del r. Okay, and I will keep that grad square intact and multiply with this constant. So h cut square by, I think I am missing yes I'm missing the e prime minus v term. It is very common that during the calculation missing a step or missing a term, because as you can see there are multiple terms, so it's fine. E prime minus v of r gradient square phi of r grad square minus h cut square by 4 m squared c squared. This is del v del r del phi del r. Okay, and finally this. Now this term is tricky because I sigma dot, what is this? This is basically, as we have seen, del v del r r cap cross this gradient I will keep and take the phi outside. Okay, let me do it as plus and keep this like this. Okay, now as you can see, there is this term can be written where, as we are dealing with the non-relativistic theory, so now I can apply the Schrodinger equation without any problem. So from Schrodinger equation we can see that minus h cut square by 2m grad square psi. Okay, this psi is not related with our theory. Okay, this psi is some random psi, is equals to e minus v of r psi. Okay, so if we take the psi as common out, then we can see that this e minus v of r is equivalent to minus h cut square by 2m grad square. Okay, so what we can do, let me box it with a different ink because it is not in our theory. We will apply this here on the first term. Okay, and what we will basically get from this part is minus h cut to the power 4 gradient 4 by 8 m cube c squared. I hope you guys will agree because this 2m will get multiplied here. Okay, and then we can write the phi of r. Okay, so this term is sorted, and now this minus h cut squared by 4 m squared c squared del v del r del phi del r. Now the tricky term, we can take this del v del r outside because this is a constant term and it won't affect our vector quantity directly inside the cross product. So we can take this out and take a 1 by r and multiply a r mod of r basically here. So r cap will give us r vector. So what we can do is minus h cut squared by 4 m squared c squared I sigma dot 1 by r. Okay, let me write here because it is a very important term. Minus h cut squared by 4 m squared c squared I sigma dot 1 by r del v del r. Now this r is basically mod r. I'm not putting the mod because it is unnecessary because I'm not giving the arrow sign over this r. And inside a bracket I can write this as r vector because mod r cap is basically r vector, and with a cross gradient with a phi. Okay, now you can ask me what is the reason of doing this, because it was fine looking like this. Why this? Because we have this constant here and we know that L vector in classical mechanics is r cross p. Okay, so what we are trying to do here is basically bring a p here, and p is basically I h cut grad minus I h cut grad. So I have a minus here, I have a I here, I have a h cut here. So I can take this term and make this as p. Okay, so r cross p, and r cross p is basically L. So we can write this as L because our primary goal is to find our interacting Hamiltonian in terms of spin, angular momentum, and orbital angular momentum and magnetic moments, because these are the things we already know about in quantum mechanics, right? So our goal will be to reach our to a certain thing that contains the values or contains the quantities that are already known to us. So what I have to do is now see p is minus I h cut grad as I have written. So if you take this minus inside and introduce a I to the power 4, I to the power 4 is basically 1, I to the power 1. So and minus to the power 4 is also 1. So what you can do is basically take this minus and I inside, and we will end up with e to the power 4 by 8 m cube c squared phi of r, and this del r was basically a grad. So what I can do, I can define a I squared here with a plus sign, or this minus can be taken as I squared. So I h cut grad minus I h cut grad can be taken, and we can write 1 by 4 m squared c squared minus I h cut grad minus v minus I h cut grad. Okay, and minus I can take a h cut by 2 and multiply it with this sigma, and we will get s, because s is equals to h cut sigma h cut by 2. Okay, we already know this. So what we can do is basically 1 by 2 m squared c squared 1 by r del v del r. This is L, as we have seen from here, s dot L. Okay. So this PVP will be plus and this will be minus. So what we can do actually is basically write this. I think I missed a minus out here. Yes, now it's fine. Minus I cut grad. If we take a to the power 4, so I to the power 4 will be 1 and minus to the power 4 will be again plus 1. So yes, it basically have no effect. So the minus will remain intact. Okay, the minus will remain intact, and if I take two minuses here, it will give me a plus, and the I square will give me a minus 1. So I can take this minus as I square, and the thing is done. Okay, fine. So please note, previously I was taking this minus inside. It's wrong. And from here we can write, this is P, this is P. So 1 by 4 m squared c squared p d p. Okay, 1 by 4 m squared p d p minus e to the power 4 by 8 m cube c squared plus 1 by 2 m squared c squared 1 by r del v del r s dot m. Okay, and now this whole term minus Hyperfine. So this is the final expression of our simplified third term. Please write it. So I will erase the board in 3, 2, 1. Now. Okay, so I have erased the board, and this is the second term we have to simplify. What we have already done here is there was an h cut by 2 mc, and I have taken the h cut by 2 into the sigma and written this as s vector. Okay, and now the simplification is very simple. Is we already know that for a constant magnetic field, A equals to minus half of r cross b. Okay, and if you put this in the A cross del, this is from classical electrodynamics and not relevant in our derivation, so I will just assume this derivation will be irrelevant, that A cross del will go to 0 and del cross A is already B, we already know. So what we will get from the second term is basically E by mc s dot B. Okay, this is the only term we will get from our second term, and this will be 0 from this condition. You can do it, but it is not necessary, and it is already from classical electrodynamics, not relativistic quantum mechanics or atomic physics. On the first term, okay, the first term was basically p square by 2m plus v of r, and with a phi we can write E by mc a dot p. Okay, minimal coupling term a dot p. Now we have to assume again that a equal to this, and E by mc 2mc rather minus E by 2mc minus half and r cross b. R cross b with a dot of p. Now a dot b cross c. Okay, a dot b equal to b dot a. A dot B equal to B dot A, so it's not a problem here. Finally, we can write that A dot B cross C equal to C dot B cross A. Okay, take this P here and take this as A. Okay? So A dot B cross C equal to C dot B cross A, and we can write this E by 2mc with a minus obviously P cross R dot B. Okay, now A equal to R cross P, so if we take the reverse it will give us a minus sign. So basically this is minus A, so what we will end up with E by 2mc B dot N. Okay, this is the term we are getting. So our total first term will be P square by 2m plus V of R. Okay, let me write a phi here for better feel, quote unquote. Phi P square by 2m plus V of R plus E by 2mc. Yes. B dot A. C dot B cross A. C is basically this. C is this. B cross A. So it's R cross A. Term is R cross A. Okay. The minus will stay. The minus will stay. Okay. And now what we can do is basically put a phi here. The entire Hamiltonian will be starting from this P square by 2m plus V of R minus E by 2mc B dot L plus this. It also has a B dot, it also has a B dot, so B dot L plus 2s. Okay, and now the third term, that is minus P to the power 4 by 8 m cube c squared minus 1 by, okay, no. I will take that 1 by 2 mc squared 1 by r del v del r as some zeta of r. Okay, and then L dot s, and the final term, which is only positive, is plus of P d P by 4 m squared c squared. Okay, so this is the now entire Hamiltonian equal to h phi. Put it in a bracket, give a phi here equal to h phi, that was equals to E prime phi. Okay, now we have to define. H naught equal to Bohr Hamiltonian. What's that? The Bohr Hamiltonian is basically P square by 2m plus V of r. Okay. Zeeman term is H Z1, that is equals to this minus E by 2mc B dot L plus 2s. Now see, if I take the B equal to 0 case, then the Zeeman term will evaporate and the rest will be present. And this is relativistic correction term. So relativistic kinetic energy correction term, that is H real kinetic energy equal to minus e to the power 4 by 8 mq c squared. Okay, the spin orbit term is basically HSO, or sometimes you can write it as HLS. Okay, minus zeta of R Okay, what I have done, I haven't defined zeta of R, that is 1 by 2 m squared c squared 1 by R del v del R. Okay, this term is basically zeta of R. Okay, and this zeta of R L dot S. One, two, three, and this 4 and 5. Okay, so this last term is Darwin term. Now this Darwin term got some internal problem, as you can see. If you try to evaluate, we will do this rigorously in the next video. Is this term is not Hermitian. Okay, and for quantum mechanics, it is very important that an operator should be Hermitian, otherwise the eigenvalues will not be real. Okay, so for physical entities and the real eigenvalues, we need our operator to be Hermitian, and this Darwin term is clearly not. So what we have to do is basically make it in such a manner, or prepare it in such a manner that it becomes Hermitian. We will call this as while transformation. Okay, and we will do this on the next couple of lectures. And this Darwin term is defined as H dar equal to P d P by 4 m squared c squared. Okay, so this is our entire dissection of Hamiltonian. Now if we want to write it in a coupled manner, I won't take a pause here, I will just erase it and write it here, because this is the last line. The entire Hamiltonian is H total, say, is H naught plus H Zeeman plus H spin orbit plus H relativistic kinetic energy correction plus H last Dirac. Okay, now if we only talk about these three, so in which manner we can isolate these three perturbation term only? By getting or by setting V equal to 0. No external magnetic field is applied. So when there is no external magnetic field is applied, what we can actually write is basically Ht at V equal to 0 case is H naught, the Bohr Hamiltonian obviously, and plus the perturbation term. This whole thing can be defined as H fine structure. So the H fine structure Fs can be written as H spin orbit plus H Darwin plus H kinetic energy relativistic moment. This is our final Hamiltonian term that we are looking for from the previous video, and now we have reached our goal. Okay, on the next video what we will do, either we will prove the origin of spin orbit term, that why the spin orbit term look like this, and prove this as non-Hermitian, and we will do the while transformation to make it Hermitian. Or I can do another thing, that is calculate the exact energy corrections for spin orbit and Darwin. From these two I will select one, and I hope you have understood today's calculation. Today's video is a very short video, and on the next couple of videos I will do, as I said, is basically this Hermitian process, these two corrections. Then I will go to the Zeeman effect, and in 3 separate videos I will do anomalous Zeeman effect, normal Zeeman effect, and Paschen-Beck effect. So with Paschen-Beck effect our fine structure calculation will be done, and we will go to hyperfine structure where the magnetic moment will come into our picture. So we will draw the diagrams also when this exact energy calculations and corrections will be done on the next video. Okay, so I hope you have understood, and if you like the video, please hit the like button and subscribe if you are new, and share if you want to spread knowledge. Thank you.